So this is lab 8, and that's the circuit, and I built the circuit right here. So we have our op amp right there, and it's being powered up, and then we have our 2.5 volt reference I made with this, and we have our LED connected to the output, and then we have our pot right there. So now I'm going to rotate the pot from 0 to 5 volts. Currently it's at 0 volts, and you can see it's very dim, and then at about halfway 2.5 volts, it becomes very bright. The intensity goes up, and it's at 5 volts now. Below 2.5 volts, it's very dim, and above 2.5 volts, it's very bright. It instantly switches from low to high. So this makes sense because this is what a voltage compare circuit is exactly what it's supposed to do. It's supposed to switch between two saturated states, low and high. So if we look at the case where our Vin, our non-inverting input, is more than 2.5 volts, which is our inverting input, then our output will be high, and it'll saturate at positive VCC, which is 5 volts for our case. This happens because our V out equation is this. If there is a positive difference between V plus and V minus, then that will be amplified, and V out will be a high output. Basically a high output, meaning it will be very bright. On the other side, if we look at the case where our V in is less than 2.5 volts, so our V plus is less than V minus, then the output will be low and it will saturate at negative VCC, which is 0 volts for our case. Those two cases completely represent this graph right here. Like, it will show where if it's saturating on this side, the high side, or saturating on the low side. And lastly, we can see that when the voltage is less than 2.5 volts, our LED is dim, but ideally it should be off. This is the case because our negative VCC is 0 volts instead of negative 5 volts. So basically, instead of saturating at the negative VCC, that line right there at negative 5 volts is saturating at 0 volts. But since in the circuit, we know it's not exactly 0 volts, it's close to 0 volts, but not exactly. So that's why it's dim. So I made the same circuit in Tinkercad too and tested theory, and it actually works. So you see how this is the 2.5 point, and if I make it, and it's less than it, and the LED is off, but in the reality it was dim. If I make it more than 2.5, it instantly switches to high, and less than 2.5 turns off. Moving on to exercise 1, I'm going to show you how I found the gain of the non-inverting op-amp circuit. So first, according to our second rule, we know that V plus is equal to V minus. So then we can say that Vin is equal to this point right here and is equal to this point right here. Second, we know that according to the first rule that there's no current flow in the positive and negative terminals. So I is equal to 0 here, and then, but there's I flowing from V out to ground down here. Then if we use KCL at this node right here, so then we know this current has to equal this current, and because there's no current going this way, so these two have to be equal, then we can do Vin minus ground, which is 0, over R1 is equal to V out minus Vin over R2, so right here. And then when we simplify, we get the gain is V out over Vin equal gain is 1 plus R2 over R1, and it's positive because it's a non-inverting op-amp. So this is exercise 2, the unity gain amplifier, and this is my circuit. So we have the pot right here and the white wire going into V plus, and then the V plus going into Arduino. Then I have the V minus going into V out, and both the V minus and V out going back into Arduino. And it's being powered up right here, the op amp, and the power rails are right there. And this is my Arduino code for that. And this is my processing code, which I modified from lab 5 and cleaned up a little bit. So this is what the processing window looks like. So we have our Vin at 0 volts right now, and as I increase it, then now V out starts following. And when Vin is at 5 volts, V out doesn't get to 5 volts, but it's close. So again, when I go back down, and so when it passes this point, V out is just stuck there. As you can see here, the circuit does not provide unity gain for all input voltages. It only has it for voltages above this point, which is roughly about 1.85 volts. And this was not expected because if you do the math for the circuit, you can see that V out is supposed to equal V in, but when we look at the processing window, that's not true. This is an equation that governs the unity gain buffer. So you see AV over 1 plus AV, that will roughly turn to 1 because AV is a large number. So then V out is equal to V in, but in our case, it did not happen. So basically the problem is that we have 0 to 5 volts instead of negative 5 to 5 volts for our positive VCC and negative VCC. That's why we're seeing that the output is not following the input for all voltage levels. And this is not an ideal op-amp situation because we're actually building the circuit. So moving on to exercise 3, inverting amplifier, this is what we have. So we have this is a circuit for inverting amplifier. And this is the analysis to find V out. So we first make V plus equal to V minus, and we do KCL, and then we find that V out is equal to negative RF over Rn times Vn. And our gain is this term right there. So in our case, we need gain equal -10. We can use something like 10k ohms for RF, and RN is equal to 1k ohm. We also need to make V plus 2.5 volts, so we can use a voltage divider with the 1k ohm resistors. Okay, so this is my inverting amplifying circuit right here. So to begin, we have our pot right here, so Vn going into the 1k ohm resistor, and then we have our 10k ohm resistor here, and that is going to V out, and from here it's going to V minus, and then we have our 2.5 voltage divider right here going into V plus, and then we have all these signals feeding back into Arduino so that we can read it. The only change between exercise 2 and this exercise is that we have to add in V plus so we can read it, and then add it to the string so then processing can read it. And lastly, the only thing that changed in the processing code is that we have to add in A3 for V plus now. So here, then we have to add it down here so we can actually plot the result. So this is our result of the circuit. So V in is at 0 right now, and when it crosses 2.5 volts, you can see that the signal is inverting because the V out is the opposite. And we go back down, then you see the V out goes back up. So you can see that's inverting. And it plateaus at roughly at like 4.2 volts and 1.8 volts. So you basically know that this is inverting because you can see that the V out and V in are out of phase. But this is not what we expected because the gain was -10. But in our case, that's not true. This is because our negative VCC is again 0 volts instead of -5. So we can't get that clear -10 gain. Lastly, the thing I want to mention is that our VN is also from 0 to 5 volts. So that is going to have an effect on how it should ideally operate in this circuit and also the last circuit exercise too. I forgot to mention that earlier. Moving on to the last exercise, the integrating amplifier. I'll show you the analysis now. So in here, we'll start off with rule 2, and we know that V plus is equal to V minus, and in this case, V plus is grounded, so V minus is 0 volts. Then we can do a KCL at node A, and so then we get this right here. Then when we simplify the KCL, we'll get down to here, which is VO is equal to negative ZC over R times Vn. Then we can substitute this in for ZC, and we get our VO is this right here. And if we simplify that with respect to time, we get this final output. So this is my circuit for exercise 4. This is very similar to exercise 3. The only thing that changed here is replace this resistor with the 4.7k ohm. Before it was a 1k, and this replaced with a 10 microfarad capacitor, which was a 10k resistor before. We also still have our 2.5 volt reference at our non-inverting input. And lastly, the Arduino and processing code stay the same to view the voltages on the graph. So this is our output for our circuit. Right now, Vin is at 0 volts, or we can refer to it as -2.5 volts. So what the integrating amplifier does is it basically outputs a voltage equal to the time interval, the input voltage of the circuit. So you can see Vin is at 0 volts right now. And then when I cross 2.5, you'll see that V out inverts because if you remember from our analysis, the gain is negative. Then we cross back down 2.5, it inverts again. It looks like a charging and discharging of the capacitor. Lastly, another thing to notice is that when V in is at 5 volts, V out is steady here at 1.8 volts.